All right, the last one. This is the final exam for semester 2, X Chemistry. We have acid, base, and oxidation reduction today. So let's take a look. Identify the following properties as acidic or basic. Slippery would be basic. Sour would be acidic. Turns litmus paper blue, base. Turns litmus paper red would be acidic. Reacts actively with metal to produce hydrogen gas. That is acidic. Define Arrhenius acid and Arrhenius base. Arrhenius acid, basically those are H plus increasers. So basically they increase the concentration of H plus. They start with H. HCl, H2SO4. Arrhenius bases end in OH, and they are H or hydroxide ion concentration increasers. Bronsted-Lowry acid, that is a proton or a hydrogen ion donor. And the Bronsted-Lowry base is a proton or hydrogen ion acceptor. So notice there are other bases that do not necessarily have the OH in their formula, but they accept hydrogen ions from water, which will increase the concentration of OH minus. Those are Bronsted-Lowry bases that may have not been identified as bases using the Arrhenius definition. Label the acid, base, conjugate acid, and conjugate base. So if we take a look, HCO3 negative has gained an H. So this is acting as a base. The NH4 plus has given off. So it's acting as an acid. Acids make conjugate bases, and bases make conjugate acids. Now notice here, HCO3 negative could act as both an acid or a base. This is called amphoteric, meaning that it can add an H or accept an H, I should say, or it can also donate an H. So this can act as both an acid and a base. What determines whether an acid is strong or is weak? The strong ones are memorized, but basically strong acids and strong bases ionize completely. Ionize completely. To figure out if a base is stronger, a weak base is stronger or weaker than another one, you look at the Ka. If the Ka, the higher the Ka is, the stronger the acid. What are 3 most common strong acids? Perchlorate, hydrochloric, and sulfuric. Others include hydroiodic and hydrobromic and nitric. We call this Brickle and the major eights. The major eights being nitrate, perchlorate, and sulfate. What are the 5 strong bases? This would be sodium hydroxide, potassium hydroxide, all of the group 1A elements, rubidium hydroxide, and then we can also include the group 2A elements, for example, barium hydroxide and strontium hydroxide. AP exam counts all the group 1A and 2A elements as strong. In a reaction of strong acids with strong bases, what do you get? You would get a salt and water, H2O and KBr for that one. Remember, a salt can be any ionic compound. Give the pH values for acids, bases, and neutral solutions. So if you have 7, if it's less than 7, that's an acid. This 7 is neutral. And greater than 7 would be a base. For pH, it switches with POH. Determine the pH. If this is the hydrogen ion concentration, well, we're going to take the negative log of this. So that would be 7. We're going to take the negative log of this. It's going to be 2 point something. So if we take a look, we press in negative log, 2.5 times 10 to the negative third. We get 2.60. Here, it's going to be 11 point something. So in reality, this is going to be a base. Negative log, 7.2 times 10 to the negative 12th. We get 11. Remember, mine's in scientific notation, 11.11. So neutral, acidic, basic. A student titrates 15 milliliters of HCl with 11.7 milliliters of a 0.850 molar sodium hydroxide. What is the molarity of the solution? So you need a balanced equation. This is going to give us H2O and sodium chloride. And notice the coefficients for all these is 1. So MaVa over Ka. The Ka would be 1 and the Kub, or the coefficient of the base, would be 1. So we're basically just going to take these two and multiply them and then divide it by that. MB times VB divided by VA. We get 0.663 molar HCl. What is the significance of using an acid-base indicator in an acid-base titration? The color change signifies the endpoint. This allows you to do it very quickly and without something like a pH meter. The pH meter will work, but this color change allows you to do it very quickly. Calculate the pH of this. Well, I have to have that memorized as a strong acid, so it's going to be negative log 0.25. 0.6, which makes sense because this would be 2.5 times 10 to the negative first, so it's going to be less than 1. Here we have a Kb telling us that this is a base. So the formula for this will be the hydroxide ion concentration is equal to the square root of the MaKa, or I'm sorry, in this case, Mub Kub. So the molarity is 0.41. The Kb is 4.38 times 10 to the negative fourth. Multiply those, we're going to take the square root of that. So the hydroxide ion concentration is equal to 1.34 times 10 to the negative second. So if we take the negative log of this, that will give us the POH. And then 14 minus the POH is going to give us the pH. So, negative log of that. Makes sense that it's less than 7 because it's the POH. 14 minus that answer. 12.13. So that is a base. Acetic acid is an acid. They want the pH. So this is going to be a little bit easier than that one. So the H plus hydrogen ion concentration is the MaKa. So the molarity is 0.75 times 1.8 times 10 to the negative fifth. We're going to square root that. That will equal the H plus. 0.75 times 1.8 times 10 to the negative fifth. Square root. That answer. There we have it. It's going to be less than 1, so we're going to take the negative log of that. I'm sorry, less than 2. And we get 1.93. I'm sorry, this would be 1.16 times 10 to the negative second. And then we take the negative log of that. And that gives us 1.93. There's our pH. Excellent. So let's take a look here. Identify the strongest acid out of these. So this is methanol. This is hydroxide. This is water. This is hydrocyanic acid. This is nitric acid. It's one of the 6. It's a major 8, nitrate. Calculate the H plus if the pH is this. To do that, we have to take the antilog, which is the second function of the log. Then we're going to take it to the minus of the 11.70. And we get 1.99, or 2 times 10 to the negative 12. The pH of a solution in which blah is blah. So this is the hydroxide ion concentration. 2 ways to do this. I think the easiest way is to find the POH, which is the negative log of 3.4 times 10 to the negative fifth. There's the POH. This makes sense that this is a base. And then we're going to take the negative log. I'm sorry, we're going to take 14 and subtract that. and that will give us the pH, which is 9.5. In which of the following reactions does H2PO4 act as an acid? So we're looking for something that is donating. H2PO4 is going to donate. So we're looking for this guy. H2PO4 makes HPO4 2 negative. So there it is donating an H to the water. So it's acting as an acid. 5, calculate the pOH of 5 molar HCl solution. So again, we'll take, it's 5 molar. Man, this is going to be big. 5 molar. This will give us the pH. Yeah. Negative log of 5. So you get this negative number. We're going to take 14 minus that. And we get 14.69, or in this case, 14.70. It is the answer. It doesn't fit our normals because we assume that it'll be between 0 and 14, but it is the answer for this question. For this weak acid, calculate the pH of the 0.1 molar solution of whatever this is. So again, Maca will give us the hydrogen ion concentration. So 1 times 10 to the negative 6 times 0.1 square root. That's the hydrogen ion concentration. We need to take the negative log of that to get the pH. 3.5. Saccharin is a weak acid if the pH of it is this, and the of this acid is pH of this molarity of the solution is this. What is the Ka? So basically we need the H plus equals the Ma Ka. We're going to square that to get rid of that, and then we're going to divide it by the Ma. And that will give us the Ka. So the first thing, here's the pH. So I need to get the hydrogen ion concentration, so I'm going to take the antilog of the negative pH. That's the hydrogen ion concentration. We need to take that and divide it by the molarity. I'm sorry, we need to square that and then divide it by the molarity, which is 1.5 times 10 to the negative second. And that will give us the Ka, 5.8 times 10 to the negative 10. That's the acid-base stuff. Let's take a look at the oxidation reduction things. Oxidation reduction. Give the oxidation number of each of these. So you have to have your rules. Sodium is always +1. Group 1As are always +1. Hydrogen is usually +1. Fluoride is always -1, right? Oxygen is -2 in most cases. So there are the basic rules. Now we have to make sure that this adds up to 0, adds up to 0, adds up to -2, adds up to 0. 2 times 1 is 2. So 2 plus -2 equals 0. -3 plus x has to equal 0. So that's going to be +3. Here we have 1 plus x minus 8, because we have 4 oxygens, has to equal -2. So we subtract 1, we get -3. We add 8 to 3, that's going to be +5. If we take a look here, the carbon, we have -6 plus 2, so that's going to be +4 to get to 0. How are oxidation reduction defined? Oxidation is loss of electrons, reduction is gain. What this means is if you look at the oxidation numbers and they go up, that's from one side to the other, they're going to go up if it's oxidized because you're losing negatives. If it's reduced, well, it goes down because you're gaining negatives. Balance the following equation using the half reaction method. This isn't a requirement this year, but if we take a look, H2S, this is going from +2 to 0. And the N here is going from +5 to, and this is 0 here. So that's -2 to +2. So there's a change here of 3, and there's a change here of 2. So we're going to be looking at something for that to be equal to 6. So the +2 here, we're going to probably put a 3 here, 3 here, and since this is a change of 3, we're going to put a 2 there. Let's see where that gets us. 2 times 3 is 6, minus 2 is 4. So what can we put here? 4. 2 plus 6 is 8, and that's going to do it. So the amount of electrons that are changing hands helped us balance that. I'll give the E0 for the following reactions. So here we see copper is losing electrons. So that is oxidized copper, yields Cu2 plus 2E negatives, and zinc is gaining electrons, plus 2E yields zinc. So copper is oxidized, this is reduced. We always take the reduced minus the oxidized. So zinc is negative 0.76. We're going to subtract from that 0.34. Negative 0.76 minus 0.34.
It's negative 1.1.
Negative 1.1. This is not a galvanic or voltaic cell. Those two words mean the same thing. Voltaic. Not a galvanic or voltaic cell because this is negative. That means it's not thermodynamically favored. Here, copper is being reduced, which makes sense because of this. And aluminium is being oxidized, which makes sense because it does not have a very high reduction potential. So 0.34 minus negative 1.66. It's going to make a pretty good battery or voltaic cell. 0.34 minus negative 1.66. 0.34 minus negative 1.66.
It's 2.
2 volts. Positive, so that is spontaneous. That is a voltaic cell. Now the anodes for these two, the anodes is always what's being oxidized. So aluminum is the anode, and that would make this the oxidizing agent. And here, copper is being oxidized. It's always what's being oxidized. So this would be the anode, and the zinc 2 plus would be the oxidizing agent. This is the same questions on the back of this. I didn't realize that, but that's okay. For the following reaction occurs in a basic solution when the equation is balanced, the sum of the coefficients is this. So if we're looking at this, we're going 2 here, and this is going from negative 2 to 0. We know this, we need 2 here. This is going from 0 to negative 1. So if we take a look here, to tell you the truth, we don't even teach this in X anymore. So let's just skip this. I don't have enough space, and it's not worth it right now. How many electrons are transferred in the following reaction? This one we can take a look, 0, and this is plus 2, and this is plus 1, and this is 0. So if we take a look here, we see 2 for the plus 1 and 0 for the plus 2. So if we wanted to, we could take iron, Fe 2 plus, and 2 electrons, and then we can take the hydrogens. We have 2 H pluses, yield H2 with a 0 here. So we're going to need 2 electrons there. So 2 electrons are lost and 2 electrons are picked up. A cell is, if we wanted to, we could also go, okay, Fe is being oxidized, therefore it's the reducing agent, and it would be the anode if this were a battery. DH plus is reduced, and therefore HCl is the oxidizing agent. Remember, it's the entire compound on the reactant side for this. A cell is set up with copper and lead electrodes in contact with this and that. The standard electron reduction potentials are this. the potential of the cell in volts. Cell is set up. So we're just setting this up. So we need to look at these two things and say, okay, this has the most reduction potential. So this is reduced, this is oxidized, 0.34 minus negative 0.13. 0.34 minus negative 0.13. That's going to be
It's 0.47.
47, which is weird because the answer, that's the closest answer to it. You could have put none of these, but yeah, I think that somebody just maybe misread this or something. But maybe I misread it, but that's what we're going with. A galvanic cell utilizes the following standard reduction halves reactions. When current is allowed to flow, which species is oxidized? Standard reduction half reactions. So this is going to be reduced. This has less reduction potential. So if we take a look here, we would flip this, and the Cr3 plus is going to the Cr2, O7 negative. So here we have an oxidation number of 3 plus. Here this is going to be negative 14, and it's going up to, I believe, plus 6. So again, from 3 to 6, this is definitely being oxidized. This would be the anode from the cell, and this would be the oxidizing agent for this. That's going to conclude it. One last thing that I wanted to remind you guys of is that all the answers are in here as well to this. But these guys right here are the functional groups. You will need to be able to identify these. The other thing is, a good thing to know would be which of these functional groups, has the higher boiling point or something like that. Well, if it's an alcohol or a carboxylic acid, it's going to have hydrogen bonding. Everything here has dipole-dipole because they all have oxygens with the lone pairs on there, so those are going to pull the electrons towards that. And all of them obviously have dispersion forces. So if you're looking at boiling point, carboxylic acid compared to all of these would have a higher boiling point. Alcohol would have the second highest, and then you basically would have to go with the mass of the other ones with the dipole-dipole to compare their dispersion forces. Remember that an alkane, alkyne, and alkene. Alkane is all single bonds, alkene is double bond, and alkyne is triple bond. Remember that if you're only dealing with these, the larger of the ones are going to have the higher boiling point because they have more electrons, which means they have more London dispersion forces. If they have more branches, that would have a lower boiling point than something that's just a straight chain. Because something that's just a straight chain, they can kind of stack on each other and attract each other a little bit better. Versus something like this is going to poke something, and it's not going to, lie as well. This is why if you're stacking logs, you take all the branches off of them, right? So this is going to kind of poke and not let something get it close enough to have a good attraction. And those attractive forces between the molecules, the intermolecular forces, are what makes something have, a higher boiling point. The more forces you have, the higher the boiling point because it takes more energy to pull them away from each other. That's going to do it. Thank you and good luck.